audio-visual automated speech recognition, and we're gonna try doing this with three people here. So my name is Haik, and I chose this paper because I'm a cognitive psychologist and my research area is speech processing. So it's kind of close, but it's not quite automated speech processing. It's how we humans do this. So there are some similarities, but a lot of differences, of course. And I'm in conversational AI track. We have Daniel who will, so I'll do basically the intro part and show a video. But you'll see interesting thing with humans. And we have Daniel who will cover the architecture of the model that was used for this paper. And he's in music moderation track. And we have Hetvi, who's also in conversational AI group with in my group, and she will cover the experiment and the results. So just some historic example for the modern automated speech recognition systems are really they've been modified and improved a lot. So initially, whenever they started in 80s, 90s, they were not as good, but currently they pretty good. And you have to remember that they were initially introduced for, uniquely for telephone speech, right? So somebody calls a customer service center or something, a bank or something, and then you can try to navigate through menus and get services. So that was the entire point. So it was never intended as audio-visual, right? So it always started with only the sound. And even though these modern systems are performing good, they still not so good when the sound is degraded. For example, it's low resolution. The system, for example, inside the Zoom, you can do automatic captioning. I think it's using the AWS Lake service, but sound quality here is using different bandwidth. It's much larger bandwidth than over the telephone speech, which uses like 8 kilohertz, right? So it's very restricted. So the resolution effect is there is also the problems arise obviously when there's noisy environment or there's variability in talker, which by this I mean when, for example, the talker is accented, if the system is intended for native let's say American English talkers, and they have a lot of training data on those individuals, but somebody is accented, and a lot of people in America are accented actually, so those systems are not performing as good. And this audio-visual model is one of the solutions. And you have to understand that the applications are limited because you can't obviously use it over the phone, but for, let's say, video meetings like this one, or there's some video enabled vending, or let's say if you're crossing a border or something, there are some systems that use primarily for face recognition, but you can also, for example, interact with them, with the system, or interaction with robots. So there are applications, but I mean the phone system is still going to be only speech. So one, again, given my background, I just want to give some information about human speech perception, and we don't call it speech, word recognition or like speech recognition, but it's perception, because all of this we use our senses, right? So we perceive the environment, and pretty much the entire brain participates, and we have both bottom-up processes, basically whatever you hear, all the stimuli, and then top-down, whatever your brain has different schemas, expectations, you know, what word is going to be said in what setting after which one, you know, or which person can talk in which way, or in what kind of, you know, language they can use. So we have all sorts of expectations and, you know, top-down knowledge in our brain that guides our perception, and not only for speech, but pretty much for anything. And the process is really categorization, right? So you have to figure out which sound is said, which word is said. So those are assumed to be stored categories in the brain, and then you're trying to match basically the input with the category. So this is, you know, close to the, and I mean, this view is borrowed from, you know, the computer model. And one interesting thing is that our perception is constant. So you have, for example, if the same word is said by the same person in different acoustic environments, you know, in this room, in another room, outdoors, acoustically, if you measure, if you look at the spectrogram, they are different. So physical phenomenon of the sound is different in different locations, different reverberations, you know, there are entire fields of study of reverberation, for example. But nevertheless, your brain treats the same sound, you know, the same category of the sound, let's say P, T, or whatever, right, is constant. So those variations are not like throwing you off, like every time, you know, the word is spoken. The same thing happens with other senses. Let's say, you know, the color of garment outdoors and indoors, depending on the light, you know, the sunlight is like a million times brighter than indoors, you know, like 1 or 2 light bulbs. So physically, if you measure in nanometers, you will see that it's really different physical phenomenon, but perceptually, your brain treats it the same. If it's a red color indoors, like the colors don't change. It will be like, think about super confusing if it was like that. You go in and out. So given this information that the entire brain participates and there are a lot of interaction of different senses, there are interesting phenomenon where even within, for example, speech perception domain, acoustic processing, you would think that's the main thing when you process sounds, does not dominate. And there's an interesting example here. So I want everybody to look at the screen and, you know, listen for first pass, and then we'll see what happens.
Ba, ba, ba.
Have a look at this. What do you hear?
Ba, ba, ba. Ba, ba, ba.
But look what happens when we change the picture.
Ba, ba, ba. Ba, ba, ba. Ba.
And yet, the sound hasn't changed. In every clip, you are only ever hearing ba with a B.
Okay, so maybe I can ask people to raise hands if it worked for them. So if you, when the picture changed, your perception changed. It was no longer ba, it was something else. You know, something like fa or va. So did it work for you? Can you raise your hand if it did? You can do that in the. So it did for most people, I think, right? And so now let's. Let's listen to the second part again, but look away, or, you know, you can close your eyes or look, you know, look away.
Ba, ba, ba.
This part is ba.
Have a look at this. What do you hear?
Ba, ba, ba. Ba, ba, ba.
But look what happens when we change the picture.
Ba, ba, ba. Ba, ba, ba. Ba.
And yet, the sound hasn't changed. In every clip, you are only ever hearing bar with a B.
So you see what was happening? Your vision was dominating your sound perception, right?
Ba, ba.
It's a one. It's one of the cues that your brain uses during conversation with the person, right? So remember, speech and language, it's all intended for communicating with people. So evolutionary developed in those settings, and you are using it to communicate with others. So which means when you talk to somebody, you're looking into, like you see their face, you see their eyes, mouth. So all of that information is basically encoded in a holistic way when you interact. So your sound perception and your visual perception are really intertwined in this case. But interestingly for us humans, this is not clear for other mammals, vision dominates, and not only speech perception, but there are phenomena you can show for all sorts of, like for tactile sensation, for all sorts of things. The vision really dominates, and vision creates multiple illusions, right? So I just wanted to give you this example so you understand that with humans, it's really audio-visual from the beginning, pretty much, right? So like the infants, they don't have as acute of a vision, but it pretty quickly develops, and then really when they acquire language, it's really audio-visual, right? For us, basically, the phenomenon is not separate, right? But for machine learning approaches, currently they're trying to improve using the visual input, right? Okay, so I think I'm gonna. So now, guess Daniel will kick in and cover the architecture.
Nice, yeah. So, like you said, talk about the architecture that the model uses, and then I'll also show a few examples, including the video we just saw. So we'll see how human-like this model actually is later on. But yeah, so the model uses AV-HuBERT, which is Audio-Visual Hidden Unit BERT. And so it trains on unlabeled data to learn the correlations between obviously the audio and then the lip movement. And it uses quite a bit less computation and data than the previous models and other models. So we could go to the next slide, please. Yeah, so what it does is it takes for the input, it takes the audio and the video streams, which are synchronized, and then it produces an AV representation frame by frame. So for the pre-training of the model is 2 steps. The first step is the clustering. So it uses the MFCC for the first iteration. And then those AV features are used in later iterations for cluster generation. And then obviously the iteration after that would still be the same. So then the second step in the pre-training is the mask prediction. And so that randomly blocks segments of the video and then tries to predict where it would assign that, where it would assign the masked frames. And then it also does the same for the audio. Could you go to the next one, please? And then, so there's also one other step in the pre-training, but that is using a clean audio and visual speech. And that's when it trains for the noise augmentation. And we'll show you the model in the next slide. Yeah, so at the bottom you can see where it does the blocking or the masking of the audio and then also the visual. So it's a ResNet transformer architecture. And that's used to try to predict the sequence of the cluster assignments, which those are, as we talked about earlier, initially done by the MFCCs, and then it's refined iteratively using the encoder, and that's done using k-means clustering. So I'm going to show you an example next, so you can just see the demo.
Yo, what's that? You know, that sounds kind of cool. And then like I'll form like a melody around it, and that's a lot of fun. Like I really.
Yeah, so the prediction at the top is what the model outputted, and this is just an example showing that adding in noise, in this case, just acoustic noise from a guitar, didn't affect the prediction at all. So the model actually focuses in on the person's lips and keeps track of that for essentially like trying to lip read, and then it can ignore the other sounds that are present in the audio clip. And can you do the next slide, please? So the video we watched earlier, we took the clip of each of those to see how this model would predict. And as you can see, it kind of acts the same way we act, right? So it sees ba, 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 but when it changes to ba, it doesn't hear it as a ba, it thinks it gets something completely different, which should be fa. So it's quite human, like, I think.
Ba, 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 ba,
Yes.
ba, 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 ba.
So it's obviously not right on the second fa fa, but it shows you how much it takes into account the visual aspect and not just the audio part. And I think Hedvi will be talking about some of the results and experiments in the next slide.
Yeah, Emma.
Yeah, are you here, Hedvi?
Yeah.
Okay.
Hi. Will you continue or I should continue?
Are you ready?
No, yeah, I told you. Maybe you can present the next two slides, and after that I'll carry.
Okay.
Yeah.
Yeah. So
Thanks.
yeah, I can cover this part. So for the experiments, I mean the data, their architecture has a couple of implementations, and in the paper they talk about like the last phase where they can use different transformer networks. But basically for their experimental setup, they used this Vox Celeb 2 for pre-training, which has a lot of hours of video, and they added noise augmentation for the pre-training data set, right? This was again we'll see with the examples later where this really helps, even though they're not really using hard noisy conditions. So this is only 0 dB SNR, which means that signal and the noise are at the same amplitude level, right? So 0 means they're identical. So if it goes into plus direction, then the signal becomes louder. So it's an easier, right? So you can hear the voice better than like the guitar sound, for example, in the previous case. or if it goes into negative direction, then the guitar sound is, you know, like let's say if it's negative 10 dB, then it's 10 dB louder than, you know, whatever person is saying. So it's a harder condition. And for, you know, the experiments, they use this LRS3. This is an AV, you know, labeled speech, and they tested it at these 5 different SNR conditions, right, to see how the AV setup versus you know, only audio setup, and the previous work is, you know, how it's working together. And, you know, their overall results again were pretty, you know, excellent. Actually, they established the new state of the art, and this was actually with and without noise. So basically in the clear as well, right? So let's look at this, you know, kind of big table. So on the left side, the first column, we have these models, and first 4 rows are, you know, the previous work, and the third column has the hours of data that was necessary to train, right? So you right off there, you can see that the previous work used significantly larger data set for training, although, you know, one of them used identical data to this one, the 433, the row 3. But if we look at the last column where the performance on clean data set is shown, so the numbers represent here the error rates, word error rates, right? The smaller the better. You can see that the new model, let's compare the AV, the, you know, for 5th and 6th row, you know, it's already outperforming most of the models, even with the smaller data set, only 30 hours. But with the larger data set, it, you know, outperforms all of them. So you can already see that it has a large advantage right there. And even the audio only condition in the last 2 rows are again showing much better performance than previous work, right? And then we can look at, you know, one of noisy conditions. For example, there were 4 types of noise used. You know, this, let's say, music and natural ones are easy one, and it's music and some natural sounds, whatever they hit. I don't know, nature sounds. But they, you know, those are the easy conditions really. The hard conditions are this babble noise, and this is kind of a cocktail party effect. You know, you have a lot of people talking. You don't quite hear each of the conversation, but, you know, it interferes nevertheless with your processing when you're trying to understand, you know, the person you're talking to. But that's not as hard as if there's a competing conversation going on at the next table, for example, which you can hear loudly. So you know, if another conversation is going and then you're trying to talk, so that, like, you understand that speech basically, right? So in my research, you know, when we use this kind of competing speech, especially if you use the same talker, so that's very hard, you know, like you're trying to listen to this conversation, but then there's another one. And, you know, if it's in your language, for example, or if you can switch the language, let's say, you know, it's the language that you don't know, it interferes less, obviously, right? So, but that's the hard condition. And then we can see, for example, you know, let's look at the speech. You know, most competitors didn't have that kind of condition, but let's look at the babble, for example, and at 0 SNR, where previous, you know, previous 2 competing models, you know, they had, you know, 25 and 42. So that's, you know, those are the errors, right? So 42% of error in identification. But when you, let's compare this, for example, to audio only for this AV-HuBERT model, then you can see that's comparable to those at even lower, actually, right? So even already with audio only condition training, this model outperforms. But with AV, you know, 5th and 6th row, so it really performing, much better. So this is, I mean, this could be used basically, right? In a commercial setting, it has pretty low. And I mean, you can see a large difference between AV and A condition. So those become clearer in the next table. And if Hetvi wants to take over, or you want me to continue?
No, I'll take over.
Okay, yeah. So
yeah. So for this table, the authors have talked about the audio-visual speech and only audio speech recognition models. So the result from both the models have been discussed in this table. It can be observed that the audio-visual speech recognition consistently performs better than the audio only ASR under all the conditions, regardless of the SNRs and the type of noise, except for where the setup where the model has been trained on only for 30 hours of label data from the scratch. Also, we can see that the table presents the model performance when the data is been pre-trained and fine-tuned for like each 30 hours and 433 hours. So we can see that the audio-visual speech is used as an input, and the model has very less word to error rate when the audio is mixed with noise. So we can see that when the only audio speech input is being used, the word to error rate is somewhere around 3.8, that is in the second column, third row. And while the noisy input has an word to error rate of 28.7, which is a bit higher, and we can say that the model is not performing well. While when we consider the audio visual speech input, the model performs considerably well with 3.3 and 7.8 word to error rate for both noisy input, which has been trained for 30 hours. So as in when the fine tuning of the data is been increased from 30 hours to 433 hours, we can see that the data, model accuracy is been significantly improved from like we can see for the last row for the noisy pre-trained type, that the audio visual word to error rate is somewhere around 1.4, while the noisy input has an audio visual word to error rate of 5.8. So basically we can say that one key takeaway from this model is that noise augmentation is needed during fine tuning and pre-training of the model. So can you please next slide please. Okay, so for basically the first figure represents the analysis for the model performance in the form of a bar chart. We can observe that the yellow colored bar indicates the performance for speech or audio speech input, while the blue ones depict for audio visual speech input. So basically we can see that when the SNR value decreases, it can be observed that the model gives best results, as also when the speech is clean without any noise, we have the lowest word to error rate. So yeah, that's it. And for the figure below that, we can we have something very similar to what the figure 1 depicts. So it basically provides the model performance with the different type of noises. We can observe that the model performance is almost similar for music and noise, natural noise type, while the model gives best results when the speech when the speech is cleaned without any noise input. So that has a good results, good results in case it has a lower word to error rate. And also we can see that the model performs poor when the noise when the input is in the form input has a speech or a babble noise. Yeah, next slide please. Yeah, so finally the table that we can see here is very much similar to that we have discussed before. The model here used by the author is the base model, which produces almost similar results as in we discussed for the large size model. So as not much importance is given to this base model, we won't be discussing much on it. And the model and the authors have used the conclusions and results based on the large size model. So yeah, that's it. Thank you.
Okay, thank